Okay, so chapter 20. Okay. So let's recap. Not just chapter 20, but let's recap a lot of what we've done so far. Essentially, the course has two major topics: confidence intervals. And what's the other one? Hypothesis testing or significance test, same thing. And we've done a bunch of them already. For confidence intervals, we started, and for hypothesis testing as well, we started with proportions. And we started with one proportion. Can someone remind me, preferably without looking at your notes, what was the formula for the one proportion confidence interval?
N over A?
What?
A over A? Is it?
That's A.
Is it Z star square?
There's no X bar in proportions.
Is it Z star?
No.
P
Sample size?
P plus or minus
P hat
plus or minus
plus or minus
Z star
Z star
square root
Square root
square root
of
of
P hat
P hat
parentheses
1 minus P hat
over N.
over N.
I finished.
So this is the formula for one proportion confidence interval. What's at the center of my confidence interval? P hat. P hat plus or minus. Go to the left or go to the right. What was the formula for the confidence interval for two proportions? Well, actually, before that, let's do the second formula for proportions, which was when the conditions for using this formula were not met. What do we call that second formula? The plus 4. So can someone remind me without looking at their notes, what the plus 4 one was? Yes?
All I remember is X plus 2 over N plus 4.
Well, that's not going to appear in the formula, but well, the N will, not the X. See, P hat is defined as what?
It's X over N.
X over N. So the X and the N are inside the P hat. So the formula that we're going to have, you're not going to see the X appearing because it's inside of something. But what is the formula? No, not even close. Thanks for playing. Yes.
Isn't it like P twiddle or?
P twiddle
Oh, plus or minus.
plus or minus. Plus or minus.
Plus or minus Z star.
Z star.
I don't remember the rest.
I don't remember the
I
rest.
think it's the same.
You think it's exactly the same?
No, it's
And then
not.
N plus 2.
No. Square root of
P twiddle,
P twiddle.
and then the same.
1 minus P twiddle
1 minus P twiddle over
N plus 4.
over N plus 4. Now, what was P hat again?
X over N.
P hat is equal to X over N. And what is P twiddle?
Our previous
X
knowledge.
plus 2 over N plus 4.
Oh wait, yeah, right.
Okay, so P twiddle is X plus 2 over N plus 4.
Wait, what was the previous knowledge? Oh, it's P0.
P 0, P naught is for hypothesis tests.
That's what I was trying to say.
Right. I believe you. So hypothesis test now for proportions. We had a null hypothesis for a single proportion. What was our null hypothesis for the single proportion? Always without any.
P naught.
Null is equal.
Thank you. P, the true value of P is equal to some specific given value of P. And what was the null hypothesis for the second one? For the for that situation? Actually, I'm not even sure we had one for that.
No.
I don't think we did, right? I don't think we did. Okay. So P is equal to P sub 0, P naught. Was the hypothesis test for one proportion. Then we went to two proportions. What was the formula for the confidence interval for the difference of two proportions?
P1 hat minus P2 hat plus or minus Z star square root P1 hat parentheses, 1 minus, 1 minus P1 hat minus plus,
Over N.
no, oh, over N 1,
over N1
and then plus
plus,
P2 hat, parentheses, 1 minus P2 hat over N2.
awesome,
Wait.
great job.
That's so.
That was it this
I
time.
meant to, like, did it.
Yes,
You get like a formula sheet for the fun.
yes, you do. This won't be on it, but you do. I'm kidding, I'm kidding. And what was the,
Wait. Oh, wait.
it's not like I'm erasing it. What was the +4 formula for the difference of two proportions?
Oh, we did 2 and 1.
Yes, we did do it.
Yes, we did the top one on the bottom. +4.
So what should I write? What should I write?
Oh, it's P hat 1 minus P hat 2.
No hats in this one. P1 twiddle minus P2 twiddle
Plus or minus Z star
plus or minus Z star
times the square root of.
square root of.
Wait, we didn't do that.
If we do.
Yes.
When?
Oh, you were sick that minute.
No, I didn't hear. I did.
So plus. Hello. Miguel, how you doing? Good. What's inside the square root?
The same thing, but.
No.
What?
P1 twiddle.
This is 1 minus 2 over N1 minus +4.
No,
No, 2.
plus 2. Because we're gonna have a total of 4, 2 here, 2 here. Plus P2 twiddle, 1 minus P2 twiddle over N2 plus 2. And these P1 hats and P2 hats, how are they defined?
X plus 1 over N plus 2.
So each one, you add 1 to the top, you add 2 to the bottom, for a total of 2 to the top and 4 to the bottom over the course of both of them.
We do an example, right?
These are all review from previous chapters. This
Wait,
is just a recap of what we've done in the past. This is not,
That's secret.
they say an camera adds 10 pounds. I usually have 4 or 5 on me at once. All right, so next, after the chapters on proportions, we went to the chapter on means, which was last chapter and this chapter. And
These formulas work. What chapters do they have?
17, 18, and 20.
What about 19?
No, not 19. We did 19. 19 was intermediate chapter for the basics for what we need for chapter 20. Now, confidence intervals again, this time for means.
So we just gonna review that?
No, we are recapping before moving forward.
Ah.
So one mean. We had 2 different situations for one mean. What were the 2 different situations? You remember? Yes? When sigma is known or sigma is not known. So what is the formula for the confidence interval when sigma is known? And what is the formula for the confidence interval when sigma is unknown? Anyone remember this from last time? Since it was like literally 48 hours ago,
Standard deviation of the square root of N.
and we're just ignoring the rest of it.
Z star plus.
No, it was N, then parentheses, and like close.
We're all close, but this is not nuclear war, so close is not good enough. That's an actual famous expression. Some general. It used to be close is only good enough in horseshoes and hand grenades. was an old time expression, horseshoes and hand grenades. I don't play horseshoes, but apparently if you're close, it's like a good thing. But hand
I thought
grenades.
you meant like actual horses, like on horses.
So, X bar plus or minus Z star
Over.
sigma over the square root of n.
I remember this.
Great. And what's the formula for when sigma is unknown? X bar plus or minus T star times S of X over the square root of n.
Yeah, I had some.
So,
I mean, I had the S of X just like one twice, you know?
congratulations.
What is S of X?
What does the S sub X mean? Can someone enlighten Peter? Standard deviation of what?
The mean.
Sample size. All right, I'm good.
Standard deviation of the sample.
So why don't we just use the sigma?
That's of the population.
So it's the standard deviation of the population. Of the sample.
Sample.
Sorry, we don't know the population.
Oh, we do, but we can't like, too much time.
So, this is what we did last time. Now, we also had our hypothesis tests. What is the null hypothesis for both of these examples?
P.
No,
One.
no,
Two.
no.
Oh, mu equals mu naught.
Mu, the true population mean, is equal to a specific value. Greater than, less than, not equal to would be your three alternatives. So this is what we did last time.
We have a question.
Yes.
So determining, so when you're doing it on a calculator, like trying to figure out, like if it's not equal to mu, if it's greater than mu, like it's situation based, right? Like kind of
Yes.
Figure it out.
From the context of the problem. Right.
Is it like keywords that we should be looking for that would?
Not really, actually. I mean, obviously, if it says something like less than or greater than, those are pretty good indications that it's gonna be less than or greater than. But it might not. If my subway example from last time,
Yeah.
you walk into Subway and you keep noticing that they're all too small, so you do a test.
Yeah.
And if that's all they give you, you have to just understand that the alternative is that it's less than 12. And that's what you care about. They didn't specifically tell you, but from the context of the problem, you have to be able to ascertain that information. Okay. So this is what we did last time, was essentially the first half of chapter 20.
Then I also hypothesis.
Well, I mean, technically, if I wanted to calculate this, maybe I should list this as well. There's a formula to calculate your Z-score and your T-score. And I guess going back to the proportions, I should have written that as well. But since it's only a recap anyways, you have it back in your notes, but since we're here. What's the formula for Z? Yes?
The Z is root n.
No?
It's,
Maybe,
X
X
bar
bar
minus mu.
dot over, mu divided by.
What?
Sigma.
H over n.
Not really. Yes?
So it would be weird to put it into a calculator like that, right? So you'd just be able to flip it over and then have it be root n.
Oh, if I was actually doing it in a calculator?
Yeah.
I mean, I would do it in 3 steps. I do X bar minus mu naught, enter, divided by sigma, enter, times square root of n, enter. Because the square root of n flips to the top.
Yeah.
And what is the formula for T?
It'd be the same thing, but with T. Well, I mean, yeah, but with the S of X instead of the sigma.
And what does giving you the Z-score or the T-score do? What's the advantage of having that information? Yes.
Well, you plug it in.
No. These hold on, buddy. This Z star and T star This is your 1.645, your 1.96. Remember those numbers that we did all? That's got nothing to do with that Z and that T over there. No siree, Bob.
Well, the Z score, you can find the standard deviation, so you can see how close or far away this from the mean,
And that gives you what?
the p-value.
How does it give you the p-value? It does, but how does it give you?
Translate the number and then it gives you a 4-digit decimal.
Not exactly, yes.
It gives you like a range of like where your true value of P would be like between, you know.
So,
Isn't that
no,
what you said yesterday?
no, I didn't. If you, what? So, your Z score lands in some location. 1.2, 3.8, whatever the case may be. The p-value is the probability of being more extreme than that. That's what the p-value is. Now, if it's a two-sided test, it would actually be at both sides. So this is only if it's greater than, if it's like not equal to, it would be, here's negative Z. It would be both of them together. The p-value for a two-sided test is always twice the p-value for a one-sided test, for ones that are symmetric, because if it's two-sided, you get the same amount on both sides. So the Z score, what you get by getting these values with the t-score, if you're using a t-distribution, you can calculate the p-value from that. Your calculator gives you both. If you do a hypothesis test in the calculator, you will see Z equals and then P equals. So yes, it's very amazing. Your yawns are so self-esteem boosting.
So the one you want is the P.
Huh?
The one you want is the P.
The one you want at the end of the day is the P. That's correct. That is the goal of the problem is P. Yes.
Where does the P fit into the normal curve?
It's the probability of being past Z. It's the shade, the probability of being in the shaded region. If that's small, less than 5%, usually, or whatever your cutoff point is, then the conclusion is,
Significant.
the conclusion therefore is,
The null is good. It's correct.
if the P is low,
It must go.
the null must go.
Shit, yeah.
Shit, yeah. Now, the next step in our evolution of understanding is what is called the matched pair t-test. So now we have the matched pair t-test. And the matched pair t-test is a special case. I know. The matched pair t-test is a special case where you have two samples. So you would normally use the two sample t-test, but the two samples are paired up. So because they are paired up, we don't use the two sample t-test. We use the matched pair t-test instead. What's an example of a situation where you have two samples, but they're paired up? So here's an example. Suppose I'm curious how much better our people are at some task with their dominant hand versus their undominant hand. So for example, let's say I'm hammering in a nail.
What? Finish. What happened?
I can't look at you all. So, suppose we have a situation, like for example, hammering in a nail. And you're curious how much better our people are at this task with their dominant hand versus their undominant hand. So one way of doing it is to get 100 people and have them do it with their dominant hand, and then get 100 other people and had them do it with their non-dominant hand and get the means and calculate the differences and see if there's a significant difference. What's a better way of doing it than having 100 people do it with their dominant and 100 people with their non-dominant hands?
Yeah. 50 people do.
Okay. A better way of doing it, or even 100 people doing both, whatever the case may be, but a better way of doing it is to say the same people do it with both hands, so that eliminates a possible confounding factor. In other words, you're matching up the samples, right hand to left hand for the person. You're matching them up. In this case, we would use the matched pair t-test, yes?
But how would that statistic work? Because it all depends if someone's right or left-handed.
Who cares? What does it matter?
What's the-
Dominant versus non-dominant, it's the difference that we care about. What we care about is the difference. So what we do there is as follows. We have our sample one data. We'll call it X1 through Xn. You have your sample one data. Let's say it's dominant hand data. And then you have your sample two data, your non-dominant hand data. We'll call that Y1 through Yn. Now, if I was to use a two-sample t-test, I go to my calculator, I put my X's in the first list, my Y's in the second list, and I do my two-sample t-test. But no, we're gonna do a matched pair t-test. What we really care about is the difference. So we compute now, is we compute the distance, the difference one, X1 minus Y1, all the way through distance, difference n, Xn minus Yn. We compute the differences. We don't actually care about the specific data points. What
I
we,
can't see, that's why I'm using this as my class.
I understand.
Wait, so you would have to like, each, like, if there's like 50, you would have to do that 50 times?
Yes. Yes.
Both hands.
And then use the one sample t-test. And then use the one sample t-test. And then at that point, it becomes a regular one sample t-test and everything is to be done as normal. So let's do an example.
Is this new material?
This is new material. We did not do this last time. We are finishing up. This is actually the last part of the chapter. So we're finishing that up today. Maybe we'll start the next chapter. We'll see. What was that? Oh, okay. So humans, this is an example on page 448 in the book. Humans often collaborate to solve problems. Well, chimpanzees recruit another chimp when solving a problem that requires collaboration. Researchers presented chimpanzee subjects with food outside their cage that they can bring within reach by pulling two ropes, one attached to each end of the food tray, right? If you pull one, the tray just spins. If you pull the other one, it spins this way, but if you pull both, you can slide it over. If a chimp pulled only one rope, the rope came loose and the food was lost. Another chimp in an adjacent cage was available as a partner to help pull the ropes, but only if the subject chimp opened the door joining the two cages. So to get the food, the chimp will need help from another chimp. Only way to get that help is to open a door to the next cage so that the chimp can come on over. The same 8 chimpanzee subjects faced this problem in 2 versions. The ropes were close enough together that one chimp could pull both, no collaboration was required, or the ropes were far apart that you needed help. The table that I'm going to copy shows how often in 24 trials for each version, each subject opened the door to recruit another chimp as a partner. So here are the results. When collaboration was needed, The first chimp got help 16 times. I'll make sure I'm reading these now. Well, first, let me copy these numbers down before I interpret what they mean. So 19, 15, 20, 24, 24. And this one, 0, 1, 5, 3, 4, 9, 16, and 20. Okay, so there were 8 chimps. The names are actually given in the book, but they're unimportant. Each chimp had 24 trials where collaboration was required and 24 trials where collaboration was not required. The first chimp, for example, got help when it was necessary 16 out of the 24 times, but never got help when it wasn't needed. The second chimp also 16 out of the 24 times when it was needed, and once when it was not needed, 23 times when it was needed, 5 times when it wasn't, and so on. Huh?
I was just saying that last one was struggling.
The last one got help pretty much no matter what. This is the Philip of the group. So the one who, I think that was a name actually. No. So the question is there a difference? Is there a significant difference? It's only a sample of 8 chips. Is there a significant difference or not? So the first thing we're going to do is we are going to compute the differences. First minus second across the board, you have to be consistent. So what are my differences going to be?
0.
Oh my God. 16, 15, 18, 16, 11, 11, 8, and 4. So these are the 8 values. Now we take out our calculator.
So are those all x1 minus y1?
Those are all x1 minus y1.
X minus.
Yeah. Now, the null hypothesis here is that the difference, the mean of the differences should be what? What's the null hypothesis? The differences, the mean, the average of the differences should be what? Well, let's think about it. We're testing to see what?
How many times chips in milk?
Not exactly, not how many times. We're not looking for a number.
Yeah,
Not even how likely.
if they
We're testing if they are more likely to ask for help when help is required, correct? If they really are more likely to ask for help when help is required, what should the mean of the differences be?
0.5.
Not necessarily. No, that's not a proportion. See what? If they do in fact ask for help more often,
Oh, greater than 12.
not 12,
Greater than 0.
greater than 0. Remember, we're looking at the differences. If they don't ask for help more when they need it, then what should the differences be?
0.
Should be 0. If they're not more likely to ask for help when they need it, then in reality, there's no difference between them. They should have the same value. If they should have the same value, then the average difference should be 0. Here's another example where they don't specifically tell you what this is, but you have to get it from the context of the problem. So we're going to do a hypothesis test with these 8 numbers. Null hypothesis, mu is equal to 0. Alternative greater than 0. Let's see what our calculators give us. I left my calculator at home today again. I think I did at least. Yeah. So let's take out our calculator. Where do we put these 8 numbers? List 1. What test are we going to use? Which one?
One sample t-test?
The one sample t-test. This is a match pair t-test. So the one sample t-test. Right, Emma?
There's only one sample t-test.
Yes, there is.
Just t-test?
That's the one.
So do we make it a yes or no?
No, all we care about are these values. We are looking at the differences.
So,
All we care about are these 8 difference values, huh?
You're not 0.
Mu naught 0.
Wait, so it's stat and then test. right?
Well, you first got to put the data in. Did you put your data in yet? You got to go to stat edit. You got to put your data in list
Put
1.
it under the free.
Put what?
It says frac
What was it, the test?
That's
T
frequency.
test. So what do you?
It says
want?
what?
What do you want? T, what do you want?
Hold on. What does it say specifically? Give me the letters.
Free, like FREQ.
Frequency, you can skip that. Just delete it blank.
So 0?
No, leave it blank.
I can't be.
Yes, you can.
No, I can't.
What is this one?
Is it T-test?
I mean, just 'cause I'm a student doesn't mean I'm not.
It says 1.
You're leaving it blank.
Can't.
Just make it one.
Professor, is it T-test?
Yeah.
What's the null? You know. This is just a type 1.
Watch out there, buddy.
Frequency 1?
No, 2. 2, not 2.
I don't know. So our p-value is what?
7.6.
No.
7.50.
P-value is 0. Sit. Get off my screen. You don't belong there.
7.66.
Stop, please.
Oh.
It's not, a p-value is a probability. How can it be 7.66? I know what it says, huh? What?
It's 7.66 times 10 to the 6.
Yes, it's very small, yes. Go to stat, go to the right to count to tests, and go down to t-test. It should be the second one. Now, what are they asking for? Yeah, what are they asking for?
How did you put out?
What are they asking for? 0,
Why is it 0?
because we're assuming that there's no difference. We're testing to see if there is a difference.
Oh,
Yes,
what about the frequency?
1.
Oh. Why don't we think it's like 1 or 2 or?
because we're not saying we think they ask for help one time more than they don't. We're testing to see if they ask for help more than they don't. If that's not true, that they don't ask for help more than they don't, then the difference is 0.
But they obviously do, as we can see by this number.
Well, but this is a sample. Just because a sample gives you a result doesn't mean you could extrapolate that to the entire population.
So this is the fancy stuff the calculator tells us.
That the fancy stuff that the calculator does gives you the p-value, and that p-value says whether or not these results are far enough away from 0 that we can extrapolate. The same way we would. It calculates a z-score and then calculates the likelihood of getting past it with a t-score.
And you can assume.
What's to assume? We showed examples in class where we did it by hand and got the same value. It's just it does it faster, huh? You should, no. Go to data, not stats. In the very top line, there's an option of data or stats. You're going to actually use the data. Okay, we're not putting an X bar. We're going to use the data itself. Yes. Am I good? Okay, yeah.
So the p-value of 7.66.
It's not the p-value.
That says p.
I know, but a p-value is a probability. How can a probability be 7.66?
Oh, it's e to the.
Yes, you have to read the whole thing. Yes, Armin,
How would not mention the effects?
it's 1.
One.
Basically, it means each of these values you're counting one time. Yes.
So the fact that it's super low p means that this is significant, so we reject the null.
P should be 0.
Well, p is 0. It's not a matter of should be. It is what it is. The p-value is 0. 7.66 times 10 to the -5 is basically 0. Right? That's 4 zeros before 7.
So the likelihood of this happening is like close to nothing.
The likelihood of this happening, if the true value was 0, is next to nothing. And yet it happened. We actually got this result. So if the chances of it happening are essentially 0 and it happened, you got to start doubting this, which is why we go to the alternative,
And what's the alternative?
that it's greater than 0.
That's it, it's just greater than 0.
Well, that we conclude the data supports the fact that the true value of the difference is greater than 0.
How do we calculate how much, like?
No, we don't do that.
Can we?
We don't do that.
Can we do it?
Not in this class.
Okay.
You could essentially, well, I mean, if the question is how much greater than 0, I would probably form a confidence interval around my X bar and take my X bar and say, I'm 95% confident that it's between these two values, right? That's probably the best way of doing it at this level, yes.
Wait, so what do we get from this? All we got is that P is some like small number.
Well, what does the p-value being small tell us to do?
Or reject the null.
That's what we get out of it.
That's it.
That's the answer. The whole question is, what do we go with this or with this? Final answer, we go with this.
So we don't care what the T is or the X bar.
We don't need those. We don't need those. The p-value is the one number that matters at the end of the problem.
Are we gonna need it in this course later?
Well, there are problems. I can say, what's X bar? What's your T squared?
Oh, but that's it, super kind of like,
Yeah, but at the end of the day, when it comes to rejecting or not rejecting a hypothesis test, the p-value is the one summary number that matters.
and all this math is just to help us find.
Yes, yes.
So if it's E to negative something, it's always equal to 0.
No, if it's 2.3 e to negative 2, then it's close to 0, but it's 0.023, which is about 2.3%. So at the 5% significance level, I would reject the null hypothesis. But what if I really don't want to reject it unless I'm really, really sure? I might drop my significance to 1% and say it's got to be underneath 1% for me to reject the null hypothesis. In that case, the same result, I would not reject the null hypothesis. So the significance level really matters. In this case, they didn't give me a significance level. But P is basically 0.00077 or something like this. I mean, whether you use 1%, 0.1%, 0.01%, in all cases, you're going to reject the null
Wait,
hypothesis.
so for the list, do I have to input L2 too, or do I? still-
No, for a matched pair, all you care about are the differences. We don't use the individual values, just the differences. Nothing. Well, you put in the first, you put in the yeses. The last column is differences, all that matter. I don't care about the yeses, I don't care.
This like both here.
Hey.
Yeah.
Apparently not for today. Yes. Essentially, if you're doing a test and each of these numbers appeared multiple times, would you really want to write them over and over and over again? If this one appeared 18 times and 42 times and 36 times. So what you can do is you can have one list that has all your numbers and then a second list that gives you how often each of those numbers occur.
So how do you know what order to put? Like, you just always put one or?
Just put one, basically, yeah. But if I was gonna use a frequency list, I would put L1 for my data and then L2 would be my frequency list. In this case, they all appeared once, so we didn't have to worry about that.
Which was so the P of it 7.66.
Times 10 to the negative 5 power. So those chimps, pretty smart, right?
No.
Yes, for some chimps, they're pretty smart.
Wait, so what we.
I mean, I think many regular people would try to do it themselves anyway, just to show that they can.
Wait, so the null was they don't need help.
The null is not that they don't need help. No. The null is that they're not more likely to seek help when they need it than when they don't.
But it is more like this.
Well, the data supports the fact that they're more likely to seek help when they need it, which means they're smart enough to recognize that they need help and to go after that help.
Say that one more time, they're what, likely?
They're more likely to seek help when they need it.
More likely to speak with you. All right.
So, questions?
Is that it?
For that question,
That's the next one.
Another one.
want to do another question like this?
Yeah, sure. Yeah.
You?
Yes, we get the hang of it.
Okay, they get the hang of it? Okay. 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 Oh. Here we go. Here's a question. Never mind, I don't like that one. Too close to home.
You just give us random numbers.
No, wait, what do you mean you click on?
Okay, here's one. Cola makers test new recipes for loss of sweetness during storage. Trained tasters rate the sweetness before and after storage. When you go to a store and you buy a bottle of soda off of the shelf, it wasn't delivered that day. And even if it wasn't produced that day. It was probably transported from some factory somewhere days ago, kept in storage for weeks before finally making it onto the shelf. And after all that time, the question is it still as sweet as it was when it was first produced? So cola companies test all their products to make sure that they maintain their sweetness.
Wait, how do they test it?
Trained tasters rate the sweetness. Are you a trained taster?
How do they taste it like after it's already packaged?
You drink it.
They trained tasters rate the sweetness before and after storage. So they store it for 3 months and then they take it out and say, here, try it. What do you think?
Oh, so they just like, like beer, like they just keep it in there?
Yes, like beer.
Take a sip.
Here are the sweetness losses. This is before minus after. You should write this down because I'm not going to. Here are the sweetness losses before minus after for the 300 tasters. No, I'm kidding. For the 10 tasters. For the 10 tasters. I'm going to just tell you what the differences are. So I'm not going to give you the befores. I'm not going to give you the afters. They're just giving you the before minus after.
Let's say it's slowly.
Okay. 2.0.
Wait, you're still the same number?
You said say it slowly. 2.0 was the first.
Can we just say 2?
Fine, 2. 0.4. 0.7. 2. Negative 0.4.
Negative. Doesn't let you put that in.
Shut up. 2.2.
Doesn't let you put it in the
People might rate it as getting game taste. What?
in the calculator. I can't put it
Oh, like that. Hit the negative sign. Not the minus sign, but the negative sign. What was the last number I gave? Positive 2.2. Negative 1.3.
Wait, what was after the fourth number? It was 2. Right, write it down.
Wait, I also lost.
Yes, writing numbers is very tough. I know. My kindergarten students have trouble. What? Sure, I will start over. You can double check to make sure that you copy these things down correctly. 2, 0.4, 0.7, 2, negative 0.4, 2.2, negative 1.3, 1.2, 1.1, and finally 2.3. Is there good evidence that the cola lost sweetness? That's their question. Is there good evidence that the cola lost sweetness. I will give you 30 seconds to do this problem.
Yes.
I'm not sure. Do you? Oh, you know? Can I see your calculator? I don't want to give it away.
You said if it's high, you let it fly.
Let me see your data first. 2.4, 0.72, negative 0.4, 2.2, negative 1.3. Okay, and then you did a test. Which test did you do? The t-test? Data, mu, 0.
What? Bro, no, he's dumb. You're wrong. Yeah.
So what's your answer?
0.01, less than 5%, so you reject the null. You did it wrong.
No, I didn't.
How much you want to bet?
You did it wrong.
Dude, I should play the
Look at
lottery.
your p-value.
Yeah, I know, that's why. It's high, you let it fly.
No,
Like
that's
Snoop
not.
Dogg. Bro, how often do you
What?
You know, Snoop Dogg is always high, you know, so you let him fly.
Like Willie Nelson.
Who's that?
Oh my God.
Like Cheech and Chong.
Like you, John. Okay. Yes. Tell them why it's the other one.
Put it the wrong way.
The p-value
Yeah,
that
but why
I
is it that
got. Oh, that's from like 20. Sorry, Steve. I just saw that from like 20 minutes ago.
Why is that one? Why? I don't know.
I didn't see your values until just now. Well, no, if you got a p-value of 0.999999999,
He's
then
right.
you're-
He's right.
guys, go. I'm recording this. Leave. Steve, if you got a p-value that big, you can't put that as 0. It's a p-value of approximately 1, but you did it the wrong way. It should have been the other way.
No, yeah, I was able to find it out.
Okay. So this one, remember, we're measuring before minus after. Right? I told you that when I read the question. These numbers are the sweetness before storage minus the sweetness after storage. Before minus after. If it did lose sweetness, then the before numbers should be bigger than the after numbers, and before minus after should be greater than 0. So the null hypothesis is that it's equal to 0 because we always have an equal sign for the null hypothesis, and the alternative is greater than 0. What's our p-value here? 1.2%, 0.012. Do we all get that? What's our conclusion? Get rid of the null. Apparently, these colas do lose sweetness. So whatever manufacturer you are of this particular product, go back to the drawing board and add some kind of preservative to your soda so that the sweetness does not go down. Yes. Why is it what?
Why is it not less than 0?
Because before minus after, if we're testing if it lost sweetness, the before number should be bigger. So before minus after should be a positive number. And therefore it will be greater than 0. Okay. Yes? Okay.
I'm still a little confused on when you would choose greater than or less than.
You have to ask yourself the following question. If the null hypothesis is wrong, which side of it is it more likely to be on? So in this case, we're testing to see if it lost sweetness, correct? Okay, if it didn't lose sweetness, then it should be the same, and therefore the mu should be 0. So the question is, if it did lose sweetness, should these differences be greater than 0 or less than 0? Well, if it lost sweetness, the after number is smaller. So before minus after will give us a positive number. And therefore it will be greater than 0. So it's the greater than. Now, they didn't specifically tell you that. You gotta recognize it from the context of the problem. Alternatively, if you tried less than 0, you would have had a p-value near 1. Anything that obvious is chances are that's not the correct way of looking at the problem. Because your p-value should be in the vicinity of the cutoff point, 5%. Right? So somewhere between 0% and let's say 10%. If you're way high to 98%, 99%, and so on, you might want to ask yourself, did I do it the right way? Or chances are it's the other way. Does that make sense?
Yeah. Wait, so like most of the time it's always gonna be greater than. Like, so,
I didn't say that. If I had done the same problem with after minus before, it would be less than. It's all about how you read the problem. Right? The same problem could be one or the other, just the way it's written. So I wouldn't make a general statement like it's more often this or that. For shizzle. So the last thing in chapter 20 is a conceptual idea, not a mathematical idea. And it is the concept of robustness. 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 What's so funny?
What does that mean?
Well, it's an adjective. NESS in English, you add on to words to turn a noun into an adjective. Like, for example, someone could be mean. What is their meanness level?
That's what robust means.
No, robust is a noun. No, robustness is an adjective. Keep up, okay? So robust, for a test to be robust, it's a property. What does it mean for a test to be robust? This is on page 451. I'm going to read it in the book because their definition is really spot on. It says a confidence interval or a significance test is called robust. I will give you a second to write that. If a confidence interval or significance test is not if, sorry, there's no if in front. A confidence interval or significance test is called robust. If the confidence level or Gee, fine, okay, I'm waiting.
Wait, a confidence interval or significance test is robust?
Is called robust, but if you take out the word called, I think you'll be okay, is robust if the confidence level or p-value, the confidence level or p-value does not change very much yeah, does not change very much when the conditions for the use of the procedure are violated.
Wait, are what? Violated?
When the conditions for the use of the procedure are violated. When the conditions for the use of the test are violated. What does violated mean? You violate the conditions for the test. In other words, you don't satisfy them. What conditions are necessary for use of the t-test? It has to be an SRS. It has to come from a normal distribution. Oh, but what if it doesn't come from a normal distribution? Don't worry. If it's mild skewness, then you can still use it if n is greater than or equal to 15. What about strong skew? Don't worry. You can still use it if n is greater than or equal to 40. The t-test is robust because the t-test allows you to overcome these problems. Your conditions of normality are violated. Not satisfied. Don't worry. Don't worry. The t-test is fairly robust. If the sample size is large enough, we can look past that. So conceptually, the only idea for this section is the t-test is a robust procedure because when the conditions for its use are violated, it's still okay. We can still get around them by just making sure other things are in place. That's all you need to know about. In all my years of teaching this class, I have never seen a question on robustness more than just the very definition. The concept of robustness is the fact that if the conditions for the use of the test are violated, You can still use it.
And the most robust test is the t-test.
Not the most robust, but of all the ones that we are learning, it is robust. Just the t-test is robust
In the context of this.
in the context of this course.
It's the best, most robust.
I have to ask, I have to think whether the chi-square is more robust or not. To be honest, I'm not even sure. Oh, we will, sure. But so far, all we've done is the Z and the T. The Z is not very robust. Okay, you don't know sigma, bam, can't use it. I don't care what, can't use it. With the T, okay, you didn't get this, don't worry, we'll get around it somehow. Yeah,
So two questions. One, so they'll only ask us the definition of robust.
I didn't say that. What I said was in all my years of teaching this course, I've never seen any question other than that.
That's pretty much what I said.
No, see, I can't promise what they're gonna ask this time around. I can only talk about past experimental data. I've never seen any question other than a straight up definition. Will the entire test be questions on robustness? It's possible. I doubt it, but it's possible. I can't answer that. Yes.
How many chances do we have left after we finish
Well, let's take a look, see, shall we?
We only have 7 classes left, right?
Yes. Chapter 21. You got to do. 22. We have to do. It's a very small chapter, itty bitty chapter. After 22, we go back and we do 6. Itty bitty chapter. And in fact, the only reason we do 6 is because we need it for 24. So 6 is actually not even any homework on 6. It's so easy that they don't even ask any questions.
Why did we do it back then?
Because you don't need it till 24. So why do it back then and have a 13-week gap? Why not do it right before we need it? People make this course are smart, huh?
So far, 4.
Yes, 4. That's it.
We have 4 chapters and 7 days. Yeah, we only got, right? 7 classes. Yeah.
It's 4 chapters and 7 classes. Yes.
We can do it.
I would think so.
You can do it.
No, we can do it. This is a team. There's no I in team. That's right, baby. But there's no I. There's a me in team. Yes. But there's also a meat in team. Like meat. Just saw that. I love meat. Quiet, mate. So what I did there? That's called an anagram. Look it up. Now, anyway. Are there any questions on this, what we did today? So listen up. I am supposed to give you time in class to do the survey that only 2 people did last time, by the way. I don't know who they are. I don't. What? You did it? Okay. Yeah, I can't have 3 people saying they did it when only 2 people are listed as having done it. Hold on, I can see right now. It is anonymous until it's not. No. Only people who are registered for the class can even fill it out. Oh, it's up to 5. How did that happen? That's crazy talk. So listen, we'll end here because I'm done. But I'm going to give you time. It's www.payattentioninclass.com. Do it. No, I'm leaving right now. Don't leave. www.csun.edu/SEF